These are the codes obtained by evaluating multivariate, particular bivariate polynomials or bivariate. But we'll talk about another property of them, which you haven't actually mentioned that of local recordability or local correction. So actually, as local correctable codes. So I don't really need to define locally correctable codes. It doesn't really matter. You'll see the example and you understand the definition. But essentially, what you want in a locally correctable code is, this is the code word. Someone had, maybe that's the message. Someone had a message, they encoded it to a code word, a bit longer. This is like sigma to the k, sigma to the n. So this is C of the message. And what you want is not only the ability to, given a code word or given an n symbols here, that are close to a code word, you don't just want to be able to figure out what the code word is. Now you want, given also an index I, to figure out what's written here. So again, so you have a message, you have a code word, and you give an index, and what you want in a code that has this property of local correction is that you want that even though there are some errors here, you want to figure out what was written in the original code without the errors at entry I, despite the fact that definitely the adversary is going to put an error here if you want to be. Yeah. So that's local correction. So essentially you want, and by local I mean, so that's correction, but essentially in local what you want is to be able to figure this out without decoding everything and computing the code back. What you want is to look at only a couple, a few, hopefully constant, a few entries of the code word, and somehow figure out from them what should be written.
So it must be strictly more than the amount of errors you allow the adversary to do, right?
Good. So we are going to use a randomized algorithm. Right. Good. So if I want anything like that, then I better use randomness. Good. Because if the adversary knows what I'm going to do, which, like, let's call it Q bits I'm going to read, he's going to put errors in those bits. So what's going on is that in order to correct this entry, like figuring out what is actually written at the ith location here about errors, I'm going to choose a Q tuple, Q for queries, Q tuple at random, maybe not completely at random, but some random. In such a way that eventually, from the adversary point of view, I'm going to read everything, doesn't know where to put the errors, but somehow in every such Q tuple, you have information about I. Now that's really structured, right? It's not random. That won't happen in a random mapping. Right? So what we want here is actually a structured thing. So probabilistic method won't help you. In particular, we don't know how good can you make these codes. But let's talk about it after we see an example. The example of Reed-Muller. So we don't know what's the best local code you can achieve.
But there are low bounds?
Low bounds?
Low bounds, yeah.
Yes, there are low bounds. I'll talk about it. But let's see one example, the example to talk about. And the general definition, I can tell you about it, but it doesn't really matter. So let's consider the Reed-Muller code on two variables. So this is FQ. And luckily, by the way, we are going to have field size Q and number of queries is going to be Q. So Q stands for query and field size, it's all good. You don't have to worry about a different letter for the number of queries. It can be Q, which is Q minus 1. So anyhow, so you remember how you define these codes? We associated a message with a polynomial, bivariate polynomial, where the total degree is the most D. Just remind you that, but this should be a reminder.
Spoiler alert, are you going to use it for the polynomial method instead?
No. Yeah, that would happen. When we talk about the PSR. Okay, so messages are like that. And remember what we use the, okay, so the rate of the code, just as a reminder, well, it's always K over N, but K, which is how many degrees of freedom you have here, is roughly D squared over 2. Because it's like, you know, how many I plus J are there with the most D, it's a D plus 2 choose 2 or something. I mumbled around with computation when I did it. And that's divided by N, so the rate is this thing. And the distance, for the distance, we use the Schwarzschild lemma when we did it. And we said, you know, two polynomials, two bivariate polynomials can agree on at most D times Q points. D is the degree other than Q squared. D times Q points. So they disagree on Q squared minus DQ, and that's the distance. Well, you divide to make it normalized, but DQ is the number of points they will agree at most. So that's the number of disagreement at least, not normal. Then I divide by Q squared just to normalize, get the relative distance. And that's 1 minus D over Q. And when you kind of plug it here, oh, and N is Q squared. Right. So it's 1/2 D over Q squared because N is Q squared. And so when you plug it here, you'll see what we got. Right, that was the relation between the distance or relative distance and the rate of the cone.
What is G?
What is?
G.
The degree.
The degree. Right, so I'm looking at degree D polynomials, bivariate polynomials. Initially it was a parameter, but then we figure out the relation. So we know that if you have a delta in mind which you want to shoot at, then you set D such that this will work. And then the rate will be this. Or maybe you want the rate, and then you refer the distance. This is a parameter. It's fixed.
I just to clarify, Q is prime or power?
Q can be a powerful one. Yeah, it will actually be useful. Let's see. Not in what we do now, but what we do in the last 10 minutes. Okay, so that we did already. But now I want to, correct locally. So what do I mean? So what's a chord word, right? So chord word is really just you have Q squared symbols that you see, and you know that they're actually coming from the evaluation of bivariate polynomial of the entire plane. But generally maybe there are errors. So what you see are Q squared symbols. So maybe you want to figure out what's written here, right? Some entries. It's just nicer to index it by to fill them. So one thing you can do again, you can just decode the whole thing and then encode to see what's written in the encoded version. But there is another idea which uses only Q queries rather than Q squared queries, so square root of number of entries. And the idea is, if you remember,
Line.
right, you choose a random line. Technically, it looks like that if Q is P, and if Q is like the power of it's weird, no one knows how it looks like. But let's imagine it looks like that. It doesn't look like that. So you take a line that goes through the points you care about. So maybe let's call this point AB. And you take a random line. So what do you mean by random line? Well, you can be a bit more. You can, okay. So the best way to do it, I think, is to consider this. This is the RS line. So A and B are the points you want the line to go through, so that's why I want it like that. B equals 0 like that. And RNS are the kind of the slopes. You could have thought of like T, comma, A, T plus B or something, but then you won't have the line that's vertical. So this is the way to get all lines if you care about it. It doesn't really matter. But these are all lines, right? So for every given RNS, the slope is essentially like S over R or something. But given RNS, this is a set of Q points in the plane, and they are aligned in a sense, right? Because when you move, they go for AB, and you take a step, you increase T by, well, I want to say you increase T by 1, you move R to the left and S up, but it doesn't really work this way, because maybe it's a field of characteristic too. So it doesn't align. But still, these are Q points. It behaves as like a line. Again, the things you want from a line, this happens. We'll see. So the idea is to choose S and R uniformly at random, I think not equal zero. Because otherwise I don't really mind. Uniformly at random, you probably don't want to choose both of them to be zero. I don't care. And the sample, the query actually, sample is query, the code word, kind of the noisy code, so you don't get deco on this line. And infer, we'll say exactly how. And the A differential. I need to tell you how. But generally, at this point, you have enough information. So this is the algorithm. So you see, it makes Q queries, which is square root of 10. It's not trivial. Right? So how do I analyze this? Actually, the analysis is really simple. So the way you analyze this, a warm color or bad. So think of an adversary. An adversary would put errors, he would definitely going to put errors here just because he can. He knows you want to read. So you put some errors here. Not too many errors, but you put some error here. Say the number of errors he puts is like, I don't know, tau times Q squared. So we are going to say, as long as tau is not too large, assume we can correct this entry. It's not quite the distance, it's something else. It's also the number of errors you're willing to tolerate, but it's not the distance which you know. It will be slightly smaller because you want to do more. But let's say there is a parameter tau from which, below which, so if the adversary puts less than 2 squared the errors we want to be able to correct. And he puts the error somewhere, and what we want is to kind of ask, first of all, what do we expect? How many errors do we expect to have on a line, or on a random line? So what do you think?
How many? Say it again.
How many? Like, what's the intersection? How many errors do we expect that there will be on a random line? Right? If there are two TQs, tau Q, right? So roughly, I mean, you should technically all these lines go from that point, so you should remove it and that's it, but let's not do that. So we expect, and actually we can write expectation. We expect to have, so it's really the expectation if T tau Q errors on LRS. So really what you really know is that the expectation of the RNS, maybe not zero, both zero, because otherwise it's a point. Just to be on the safe side. Of the line intersection with this bad set errors. Okay, you know that this is a tau Q roughly. Maybe you can do 2 tau Q if you care, but it doesn't really matter. And so, but I don't want that. I want to bound the number of errors. So what can I do? I'll move from expectation to bounded probabilities. Markov, right? When you don't know nothing, when you know a lot, you use channel. When you don't know nothing, you use Markov. So the probability of the choice of line, the number of errors in the line. Let's continue with this. The probability that this is more than like, let's for some parameter epsilon, the probability that you'll be more than 1 over epsilon times the expectation is most epsilon. Right, in general, if you have a random variable which is not negative, this, and it has an expectation like 4, whatever mu, when the probability that you hit like more than 5 times mu is most 1/5. Because otherwise there is too much contribution to the expectation and it's positive, so it cannot be right. So right, if this was larger than epsilon, the expectation would have been larger than tau times. Right, because with this probability you get something that's more than epsilon. Okay, good. So we know that with this is a parameter, but except the probability epsilon, which captures our inability to correct, but anyway, we can think of it as a constant. You won't have too many errors on the line. Okay, then what? So we don't have too many errors. Okay, what if we didn't have any error at all? But you wouldn't know that, so you don't know how to just say it. What would you do? So again, I promise you that on the line there are no errors, maybe except here, so that you won't just need it. How can you call this back?
You look at every D plus one subset and
Right.
then you take the majority of what they say.
But maybe Q is large. So
Oh, so just take random D plus one
okay,
points on the
so what happens when you take the polynomial that you got and you restrict it to the line? What do you get? So you have this polynomial here, and you literally restrict it to the line. So you consider instead of x, you write a plus rt, and instead of y, you write b plus st. What kind of polynomial do you get? R and S are fixed, right? Fixed, a good line. I mean, with good probability, I got a good line. Namely, I'm fixing R and S. And when I take my polynomial and I restrict it to the line, I get a polynomial in T. Right? So let's call it maybe F. It depends on R and S and so on, A and B, but F of T is really this polynomial. RT plus A plus RT. The I, B plus ST to the J, I plus J plus D. And as a polynomial in T, what can you tell me about it? What is it?
degree.
Right. So the degree of F is at most D. Because the sum of the degree, the total degree of the by polynomial is D. Mostly. And we know that, well, that's actually Reed's homework. We know that degree D polynomials cannot agree too much with each other. Right, so more concretely, we keep that here. So we know that two polynomials of degree D on this line will agree on at most D points. So we will disagree on at least Q minus D points. And so in my head, I'm like, this is one polynomial, this is another polynomial, and their distance is Q minus D. This is one sum, one F, and this is another F. Not it's the limit, just another F. And the distance is Q minus D. And the number of errors that we are guaranteed to have when the line is good is at most tau Q over epsilon. So if tau Q over epsilon is sufficiently small, smaller than Q minus D over 2, so from F it can only get you this far, not that far, but not that, then at least information theoretically you will be able to recover not the entire polynomial because you didn't read it, but the polynomial here. And then you can get this point. So if this holds, we can infer, as in step 3, we can infer the code law at AB. And because if the line happens to have few errors, fewer than half the distance between any possible other degree polynomial, then we can infer if there are efficient way of doing that, by the way, but it doesn't matter to us. At this point. There are good ways to decode the internal, of course, otherwise it would have been such problem. Good. So this means, let's just do the calculation. It means that as long as D is at most 1 minus 2 tau over epsilon Q, I multiply by 2 and begin. And we are happy. We're able to decode. Right, so it's really similar to what happened here. So here we chose D. If you look at this for a second, here we chose D such that D is, if you just remove the 2 and the epsilon, it's exactly what's in here. So I mean that under this premise, we can locally correct, and the rate, just to compare it to, the code as a code rather than as a locally correctable code, the rate is half D over Q squared, but D over Q squared is this. So rather than have 1 minus delta squared, which we have here. That's what I'm saying. So you see, you can actually locally correct. Think of epsilon as a constant. We know that you cannot define error correction, error reduction. We did it for languages, but we can do it as well. All right, so without any essentially loss in rate, we can actually locally correct. Okay, questions?
Can we actually use the majority when you said the condition? Or
No. Use the Reed-Solomon decoder. Right, it's something else. Because you can probably, I mean, you have the polynomial. Okay, you are given the evaluation of a polynomial on the line, except for a few points. So you can't do majority because you probably see Q different symbols. There are Q symbols that you can see, and there are Q symbols that you see. So majority won't do, but it's not
By one, you have enough. Like you
Okay.
could do,
you have Q points here,
right,
and there are Q possible points. So probably everyone will appear once, twice,
if possible. Oh, I see.
but it's a Q. No, it's not like there are 2 options in the field and you see Q there. You have Q options and you see Q there. So, but you need to decode. There are ways of decoding. It's not trivial, by the way, how to decode. It's really cool. But at least information theoretically, we know that we can. And you see, what happens here really is that, I mean, it's not a random thing. There is a structure. Right, so in this case, the structure is that these contain many codes. Like in every line, you have a code. So, so I want to tell you 2 things about it. First of all, what's known. It's actually very interesting. So you can immediately get like this is square root of n queries. You can get them to the 1/3, taken a cube, and so on. And that will won't go well asymptotically, but using the derivatives also that we talked about, and that's why they were introduced to me, you can actually get, and it's really nice, a code with a number of queries, just at the side, okay? You can actually get using derivatives and high order derivatives. You can get 2 to the square root of log n queries. Roughly, 2 to the order of log n queries. It's a polynomial, it's really good. But the distance or the relative distance is non-constant. It happens to be 1 over 1. It's not trivial. I'm going to do it, but I can do it. And then using expanders, you can actually amplify the distance to a constant without hurting that too much. It will be larger, it will have the same asymptotics. And these are the best codes we know.
What is the first round?
This delta of queries. Delta of queries is a polynomial. Well, it's this thing. Distance is bad. You can amplify the distance using expanders in a non-trivial way to get that. That's the best we know how to do. The lower bound is omega of log. So what do you mean? If you want a code with constant distance and constant rate, like good code, you need to do log n queries. Not too true now. I'll show you that. And so we have this gap, which is quite substantial. However, if you are willing to relax the notion, just fun, it's actually not for many applications, so that you can also kind of abort. And you say, I don't know. So just to be clear, if you are given a code word, a valid code word, you shouldn't be paranoid, you should never abort. But if there is even one mistake, you can abort, and that will constitute a 16. You don't have to actually correct. it's enough to say abort, or if you don't abort, output the right. You have probability as here. If you are allowing for that, then right, so it's an easier problem. So the lower bound you expect to be lower, it is, because it's harder to know. So that's called the relaxed locally correctable code. I'm just telling you the, nothing for it. So it still requires super constant number of queries, but we know how to do it with log square, almost log n square queries. That's little form. So for relaxed, we know how to do much better. This is really new. But for locally correctable as this, there is a really beautiful question. Can you narrow this gap? Or what's the right answer? Even no one really knows. You see, we don't have the probabilistic method to tell us what's the right answer. So it's structured. I don't think wonderful. Anyhow, so this is that. Questions about Reed-Muller as a locally correctable code?
What of the previous
Yeah.
bound?
So it's actually very interesting. It started with log n to the log n, and then moved it to the log n to the log n, and then star, and then no, it was 69, and then it was log n squared. That's like maybe 5 minutes.
I think like the middle gap is the interesting.
This one,
Yeah.
that's the big place. That's the one thing we didn't do. So the breakthrough was done by us, but all of the others. Yes. Right, but it's really close. So I mean, I think it's kind of interesting. Once you allow this relaxation. Interesting when you allow this relaxation, these codes are more resemble what are called locally testable codes. Does it say like that if you know now?
Locally testable codes, they have much higher lower bound.
No, you can do it with constant.
Oh, really?
Yeah. And we may talk about it at the end. Sure. The construction of those uses K graphs in a very nice way. So, kind of two groups together. It's really nice.
Locally correctable and locally decodable is the same.
Right, yeah, essentially. But locally testable is different.
Do we expect the lower bound to be log n squared or like log n
For RLCCs or
for RLCC?
I don't know. So the lower bound, when you look at the paper, it's kind of really captures what's going on. So I'm more and more thinking that maybe that's could be the right answer. But you get it up square, and for the other bound, it's really unclear how to get it down below log square of n. So you need a different idea if possible at all. I don't know. And even here, the gap is larger, and some people from data structures, they have reason to believe like the application to data structures, and from that point of view, it seems that they don't believe this little bound again. I don't know. We don't know. We don't know interesting stuff. We know that to get not that, but much smaller queries than those, you really need to construct terrible codes, and that will be enough. So you can really relax the conditions. It doesn't have to be constant rate, it doesn't have to be constant distance. We can patch things up afterwards. So that gives you some intuition, maybe that's something correct. I don't know. It's like one of my students is thinking about it for 4 years, right? So yeah. We should ask him what he thinks also, but I think let me tell you one more thing about this, which is kind of a curiosity, which I think is really nice. What happened here in this analysis is that, the reason you took total degree 2 polynomials, total degree D polynomials in 2 variables, is that they had this property, obviously, that projected to a line will give you a degree D polynomial. And you can ask the question, which the answer seems to be no. Are there more functions? Maybe you can gain more functions that maybe they are not total degree, but when restricted to a line, they give you a degree D polynomial or less. Maybe somehow things cancel out. The answer is no, definitely no. If you feel like real or competent, the answer is definitely no. It doesn't work this way. I mean, you can define the notion of a degree by asking what's the, I mean, that's how you can define degrees, complicated creatures. But the answer is yes, if the field is of low characteristic. So it turns out that the characteristic kind of, if it's like true, for example, that's clear, cancellation occur like in the field, like in the context of the field, not in the context of the operation, like the traditional multiplication, as you might imagine. So it turns out, for example, when we do the calculation, that there are actually most functions when restricted on Q squared interest, when restricted to a line, have a non-trivial degree there. So the trivial degree is Q minus 1. Every function can be computed by a degree Q minus 1 polynomial in that Q, because x to the Q is x. But if you just say I want something non-trivial, so I want degree at most Q minus 2, then you can take it forward and get some applications. Q minus 2, then most functions have this of F2. It's crazy. I walked in the middle of the lecture when they said that, and I didn't heard the F2 file, and I just raised like that's not true.
But I mean, that's some of the beauty of probability theory, because that you might get that for most cases they are like non-trivial, as you say.
No, but it's not probability. It's like you shouldn't expect. I mean, I'm going to contradict myself in a second, but still, the lesson is that you shouldn't expect that if you have a degree, total degree K polynomial here, a random line will hit it. I mean, the projection will give you a degree K. That's kind of how you define the curves. So it's weird that like globally you have high degree and locally you have low degree. It's a weird thing. It's a property of small fields. Like it's not. I mean, you shouldn't feel comfortable with this. Right? You should feel like I'm lying.
But it's not small fields. You said
it's small characteristic. Right, small characteristic. Yes, yes. So something about the characteristic makes things cancelled in a non-intuitive way because we're not used to work over F2s. So just to exemplify this, let me just do the simplest case. It's all the same. And again, you can take this idea further and actually construct interesting codes, locally correctable codes, and so on. I don't mind that now. I mean, it's not more found out. I mean, the signals. So, okay. So the question is, let me be specific. Which like functions, but let me write them as polynomials. Which polynomials? But it's a general function. F it's y, Q it's y. So bivalent polynomials have the property, real property, that when restricted to any line, because you want to choose a random line, has degree. I can say D and ask as a parameter of D, but let me just say Q minus 2. Because Q minus 1 is obvious, Q minus 2 is something. Something interesting is happening. Because a general function won't have degree which is less than Q minus 1 to be general. And of course, all polynomials of total degree at most Q minus 2 have this property. But that's roughly half. You know the 1/2, but choose 2. That's roughly half of the functions, right? Because it's like Q minus 2 plus choose 2, something like that. And I think it's exactly that. So that's half of the functions. I claim that most of the other half are also. Okay, so the question is clear. Okay, so let's see. So let's say you give me a polynomial. And I don't know which are the kind of which are the monomials I can use. So let me write it as I. So definitely I will contain all monomials for which I plus j is at most Q minus 2, but maybe more. So let me call it I for a second. So the polynomial may look like If you look like this, I want to figure out what's the I can choose, the largest I possible, so that when restricted to any line, it gives me a degree at most Q minus 2.
So you're demanding that each monomial by itself restricts to a
No,
degree? Okay.
no, no, just when you, like, when you project it to a line, and you see, let the dust clear, and see what's the coefficient of, t to the Q minus 1, I want it to be 0.
Yeah, after the sum.
After, yeah, exactly. So the test is, for any line, and just, because it's late, let me do it only for like non-vertical, excluding the vertical line, it doesn't even matter. It's just because I'm lazy at this point. Right, so that's a line. You choose A and B, A non-zero and B. And I want this as a polynomial in T to have degree at most Q minus 2. So let's see what does it say. It says about, what does this say about the coefficients I can choose, like the i's, non-zero coefficients. So this is, let's just plug it in, see what happens. Let me just run over all I and j, and then I'll figure out what's I. So it's Cij, t to the I, at plus b, j. And of course, what I will do now, this thing. Open this, right? And again, we want to exchange something. So Cij, t to the I, I'm gonna have a sum here, but you should be a bit careful when I'm writing things, when I write something like this. I mean, everything's okay, but I just wanted to make sure that you understand what you're writing. Like I would just use the binomial, everything's commutative, I'm not lying. But when I write j choose k, it's over F2. Right? It's like I'm adding once. Usually it's 0. That's the point. Right? When you open this up, it's something combinatorial. It's how many times you see 80b, that's the coefficient of thing. So this thing is it's either 0 or 1. Right? Good. And it's, as we'll see, it's actually usually 0. But so now looking at that, you can ask what's the coefficient of t to the q minus 1. So let's denote it like that, the coefficient of t to the q minus 1. What's the coefficient? Well, you have to sound I, because there are many ways to do the I here, but this thing has to complement. So k has to be q minus 1 minus, right? So I'm going to sum this one. I'm going to sum over I. As far as I'm concerned, it's from 0 to q minus 1. Everything can happen. And then I have Cij. Cij. Ti, it's not part of the coefficient, of course. And then the k has to be taken to be q minus 1 minus I. And you might want, you only sum up to j. Maybe if you sum larger than j, you can kind of remove the j. And don't worry about it too much, because that will anyhow kill it. J choose k when k is larger than j is 0. Even in F2. Doesn't. So I mean, you don't have to worry about, come on, k goes only up until j. So maybe I can't take it to be q minus 1 minus r or something. It's fine. You can take it all the way. That will make sure everything's written correctly. Sorry?
Can you say it again?
Yes, so I'm saying, I mean, what I want is to, I want I plus k to be q minus 1, but k may not necessarily go up to q minus 1 minus, because it goes up to j. And I don't want to think about that in like split two cases. But the point is that you don't have to, because even if you increase the sum like artificially up to q minus 1, it will actually be still 0. Because j choose k is 0. Meaning k is larger than 2. Right, so it's just a technicality that you don't have to, that says that you don't have to worry about stuff too much. But now continuing still, the coefficient of t to the q minus 1 is this. going over all I and j. Yes, we don't know yet. And then k is q minus 1 minus I, right? So it's a j, q minus 1 minus I. And then you have, so that's I don't have to write, but then I have to write these two which describe the line. A to the k, and k is q minus 1 minus I. And b to the j minus k. Okay. That doesn't look promising. If you want this to be 0 for every line, it means that you want this to be 0 regardless of what A and B are. And then it says that you can't even look at that. You have to look at those. And so what you really want is this to be, this won't be, this to be 0. This is the message. So you want this to be 0. So the I and J's that you can take are essentially exactly those for which this is 0.
So it is, when you're going back, you are actually kind of, okay, but you didn't start from this lemma, but you conclude that you have to go by monomial and not by the sum.
Ah, I see, yes, yes. The basis is going to be the basis of like standard monomial. Sorry, but in the analysis, I'm going to look at it. You're right. Yes, yes, yes. Good. Right. So I'm going to take a subset of the standard basis. You're right. So our I is going to be exactly all of those I and J. Now they have to be like between 0 and q minus 1. It's not like their sum has to be post q minus 1, or just both them, such that J choose q minus 1 minus I is 0. Everything in the field, 0 in the field. The field may be that large, but this is an integer, so it's either 0 or 1. Just how many times you add 1. For example, if I and plus j is really are smaller than q minus 1, the sum is r, okay, it's not so easy. But this is the number. So these are the monomials. These are some of the, we'll take x to the I, y to the j as a basis element, as long as this. The question is how many of those do you have? I mean, it's not clear. Yeah. But the cool thing is that, let's write j in base 2. Right, so j is a number. It lives in, it's between 0 and q minus 1, as we said, also I. And q is some power of 2. So you can do it for the different. Basically, let's do 2. So let's write I and j in base 2. So let's write j on top. So j, you can write it as like j0. And that's the next bit, j1, all the way up to j, I think n minus 1. Now, q minus 1 minus I, what is, in terms of bits, what does q minus 1 does when, what are the relation between the bits of I and the bits of q minus 1 minus I? Q minus 1 is, this is q. So q minus shift. It's right. You flip all the bits, right? Because q minus 1, like 2 to the minus 1, is they all 1, 1, 1, 1 vector of bits. So when you subtract that from that, there are no carries going around or something, just to flip the bits. So q minus 1 minus I is, let me denote it like that. You flip the first bit of I, the second bit of I, the last. And now I'm going to state a theorem, which you can actually prove in one line. It's called Lucas theorem. So it says that if you have, in general, if you have like form like something like that. I think if you have A choose B, and you write A and B in base P for prime P, like we do here for 2, then modulo P, it's enough to take like the binomials of the corresponding bits. So you write A in base 2, and base P, B in base P. And if you only want, the only information you want from them, it's a big number. The only information you want is the modulo P of those, it's enough to work in the number in terms of bits and multiply. It's really cool. kind of crazy. In particular,
You're not talking?
No.
One sentence.
it's a one sentence, I don't remember. That's one sentence.
Again, modulo P,
Yes, that's a,
yes, subtriangle.
right, so for any point. We will use it for two, but for any. There are a couple of proofs, one of them is one line. I don't remember that.
So you just need that one of these is zero.
Right, exactly, good. It's just the, how many, so A and B are both P to the n or something, P to the n plus one. Just how many bits, like P symbols, you need to represent A and B. I mean, here you write A and B as,
Q is 2 to the.
right. Oh. Mm. You take the largest. When it does really matter because you have a zero at the top. Well, that depends. It will be a large. I mean, if A, actually, it's a good question. If A is smaller than B, then B will have a bit, or not bit, a BI that doesn't have a corresponding AI, then zero. But we're always under the agreement that a number choose a larger number is zero. So it also corresponds to, it makes sense in that sense. Okay, so using Lucas's theorem, you can immediately see what's happening. So what you want from J, I mean, you want this to be zero. So this means that there must be some J, some bit in J is zero, and the corresponding bit in I is one. Right, so this would be zero. The only way that this is zero is that the product is zero, and the product is zero, I mean, everything is like one choose one choose zero, zero choose one. So you want a zero above and a one at the bottom. Okay, so let's count actually let's do the diversity. So the number of pairs I and J all together is 4 to the n, which is of course E squared, without any relations to anything. And if so I want to count how many pairs like that you have where there is a zero at the top and J and one at I. So I'm just using the kind of the complement. So now I'm counting how many I and J's we have so that there is no one here and a zero here. So if there is no one here and a zero here, and if you think about it, the only things you can use are the 0, 0. And you can't use 0, 1. So you can use 1, 0 or 1, 1. So when you construct these two vectors of bits of I and J together,
It's 3 to the.
exactly. You can use each of those independently, so it's 3 to the n. Which is, whatever, I don't know. Okay. I don't want to go into the log to the basic way or something. But you see, it's like, it's essentially, this thing is like 1 minus literal of 1 x. You can write, it's a q squared minus q, or the base of 4 something. But, most functions have this property. That's crazy. Square. Square. Yes. Otherwise, it's legal.
Yeah.
And with q squared over 2 is obvious, and that's. By the way, the fact that okay. So anyway, you can actually use that for you're not asking for q minus 2, asking for lower degrees and ask how does it iterate, and it's still close to q, but not too much. So at some point it breaks. So it does give you a nice code with high rate, but they are not the best codes that we have. It's just a really nice thing that happened in finite fields that I thought we should. These are not the state of the art. But you can make from those good codes comparable to what was known. Okay.